We've seen that we can find volumes by stacking a bunch of areas on top of each other and integrating those areas to build the three-dimensional volume. The question then becomes, how do we generate these cross-sectional areas? And if there's symmetry in the problem, then that's great. Here we have spherical symmetry. We're going to generate volumes of revolutions. Here we find the volume generated by rotating the function, the square root of x. So let's go ahead and draw that. That's the square root of x around the x-axis. So right there is my x-axis. So I'm going to spin this graph in a circle around my x-axis between x is equal to 0 and x is equal to 4, which the y value, the square root of 4, is a 2. So I'm going to take that curve and I'm going to spin it in a circle. And it's going to generate something like this. There's my x-axis. So let's find that volume. And I'm going to think of this volume as taking these lines and then spinning them in a circle like this. So those circles are going to have areas that are dependent upon where we are on the x-axis. Right? Here's a tiny circle. Here's a big circle. So the area is going to be the area of a circle, which is pi r squared. The r here is that radius, but the radius is the distance from the square root function to the x-axis, which is just the value of the square root function. So I'm going to take that radius and square it. The areas of our cross-sectional circles are pi times x's. Oops, I already wrote down my pi. Cool. So now we're going to take those areas, pi x's, and integrate them from the smallest circle to the biggest circle, from x is equal to 0 to x is equal to 4. So when we do this, we have an antiderivative of pi x squared over 2 being found between 0 and 4. At the lower bound of 0, we get 0. And at the upper bound of 4, we have 16 divided by 2 is 8 pi. So the volume generated by spinning the square root function around a circle, or in a circle around the x-axis, is 8 pi.